This lesson is a direct follow-on to the lesson on set operations. In this lesson, we're going to introduce the concept of a disjoint set, and we're going to show you why it's useful for counting. We would say that two sets are disjoint if they have no area in common. So for example, these two sets are disjoint. Now, I'm not drawing the elements inside the sets anymore, but I want you to imagine that every single element that's in this set does not appear in this set, and vice versa. If these two sets have no common elements, then we can say that the intersection of the two sets is the empty set. In other words, if you were to try to intersect this set with this set, there is actually no element that appears in both. Now I want you to imagine for a moment that we had 5 things in the set A, and then we had 4 things in the set B. Well, if that's the case, then if you were to add the cardinality of set A and set B, you just get 5 plus 4, or 9 in total. So therefore, if the set A and the set B are disjoint, then counting them is actually really easy. If you were to take the union of these two sets, then you would get A or B, and the number of elements in A or B is just the number of elements in A plus the number of elements in B. Now, it's so useful to be able to just add up the cardinalities like this, that even when sets are not disjoint, or in other words they overlap somehow, we still try to rewrite them in terms of disjoint sets. Okay, so counting the number of elements in two disjoint sets is pretty straightforward, right? But if we have two sets that are not disjoint, we'd like to learn how to do this as well. So this time, we have these sets A and B, but they have this overlapping area over here. If we wanted to figure out how many elements there are in A or B, then we're going to have a bit of trouble because we have to deal with this overlap somehow. So before tackling the whole set, how about we just look at A alone? I want to first think about how we can actually break A into two disjoint parts. If you think about it, there's actually a piece over here, and there's another piece over here. So if you were paying attention there, I hope you saw that this set A can be broken up into two parts. First we have this part over here that I've drawn there, and we also have this part over here that I've drawn over here. Now, if you remember your set operations, I hope you remember that this section over here is the section A and B, because every element in this section is a member of both A and B. Then we can also say that elements that are over here are members of set A, but they're not members of set B. So therefore, we said that this section over here was called set A without B. So just to reiterate this, we can say that set A can be broken up into A and B or A without B. But if you think carefully about this, an element that's in A can either be a member of set A and B or a member of set A without set B, because A without B contains nothing in B and A and B contains everything in B. And therefore, we can immediately say that A and B and A without B are actually disjoint sets, because they have no area overlapping, as you can see in the pictures. Now, because A and B and A without B are disjoint sets, then the cardinality of A can just be the cardinality of A and B plus the cardinality of A without B, because you're either counting the elements here or the elements here. Now, just to avoid this being too abstract for too long, let's actually do a concrete example where you can actually see why this would be useful. In this problem, we're told that Alice and Bob are collecting a bunch of cars. Alice has exactly 14 cars, and 8 of those cars Bob does not own. So if that's the case, we'd like to figure out how many cars they both have in common, or in other words, how many cars do they both own? So I want you to imagine that in this circle over here, we have all of Alice's cars. We know that Alice has exactly 8 cars that Bob does not own. And because she has 14 cars in total, then we know that in this area over here, we just need to put 6 cars, because 6 plus 8 is 14. And that's exactly what this rule over here is saying as well. Let's copy it to see that. So we can see from this symbol that the cardinality of Alice's set, which we know is 14 cars, is equal to Alice and Bob plus Alice without Bob. We know that Alice owns 8 cars that Bob does not own, so the cardinality of Alice without Bob is this 8 over here. And therefore, if 14 is going to equal something plus 8, then that something has to be the number 6, just as we discovered from the picture over here. So therefore, the number of toys that both Alice and Bob have, or in other words the cardinality of the set A and B, is just equal to the number 6. Okay, so now I hope you understand this rule. Let's move on and see how we can do the whole set. Now in this case, we'd like to count the number of elements in all of A or B, which is this whole area that I'm highlighting here. So after breaking this all up into disjoint sets, we can say that any member of either A or B is either a member of A and B, which is over here, A without B, which is over here, or B without A, which is over here. Now again, because we know that all 3 of these sets are disjoints, then by our rule over here, we can just add the cardinality of each one by one to get the cardinality of the left. Now if we wanted to, we could stop here because technically this is true. The cardinality of A or B is always equal to the cardinality of A and B plus the cardinality of A without B plus the cardinality of B without A. Or in other words, to find the total number of elements in this whole area, you just add the number of elements in this area, then this area, then this area. However, there is a slightly easier way to actually do all of this. Since we know that the cardinality of A is the same thing as A and B plus A without B, then we can actually rewrite A without B in a slightly simpler way. If you think about it, this area, A without B over here, is just what you would get if you started with the whole area A and then took away this area A and B. So I've drawn this really sketchy because I'm going to get rid of it in a minute, but the whole idea is that this A without B is the same thing as A minus A and B, so we can replace it right over here. But then if you look carefully, notice that A and B just cross each other out, because if you add a number, then subtract it again, you just get nothing, so these two just cross out. And now it looks like we have a formula that's actually pretty simple, but we still have this B without A that I also want to get rid of. Now if you look at this formula that we talked about here, there's nothing special about putting the A without B first. So how about I swap all of the A's and B's in this formula as well? Now this formula actually works just fine as well. We can say that B without A is the same thing as all of B minus this part A and B again. And if that's the case, then we can replace B without A for B minus A and B. So now we've come to the final formula that I wanted to show you. If we wanted the number of elements in either A or B, then we have to take the number of elements in A, which is all of this, then add all of the elements in B, which is all of this, and then we actually have to subtract the part that overlaps. Now I don't need any of this anymore, so I'm going to get rid of it too. There is a slightly easier way to think about this formula over here, rather than going through all of these steps, and I'm going to show you that just before I give you an example. I want you to imagine starting by adding all of the elements in A. Well, because A is made up of 2 disjoint parts, you have to add up all the elements in here and all of the elements in here. After this, you can go ahead and add all of the elements in B as well, but B is also made of 2 disjoint parts, so we have to add all the elements in here and all of the elements in here to get all the elements in B. Well, if you wanted the total elements in this whole set over here, then I want you to realize that you've just double counted this section in the middle. So what we need to do is we need to remove one of the times where we counted it. So we go ahead and subtract A and B to get rid of this part over here. And then you've counted each disjoint part exactly 1 time. Okay, so now that you understand this formula, let's go ahead and do an example together. So suppose we know that a group of 30 people like sports, and of these, 15 like swimming and 20 like running. How many people in this group like both swimming and running? So I want you to imagine that we have exactly 15 people that like swimming, and then we have 20 people that like running. We want to figure out how many people belong to this group over here that likes both swimming and running. We know that the total number of people is exactly 30. Now, solving this is actually pretty easy. We just have to apply this formula that we just came up with. So instead of using A and B, this time we have to say that S or R is the same thing as S plus R minus S and R. So if that's the case, we know that S or R is the same thing as 30 because we have 30 people in total. S is the same thing as 15 and R is the same thing as 20. And we know that 15 plus 20 is the same thing as 35. And therefore, if 30 equals 35 minus some number, then that number has to be the number 5, right? So that means 30 equals 35 minus 5, and therefore S and R is equal to the number 5. And now we should just sanity check all of this. Since we know that all of this has a cardinality of 15, and this is 5, then the number of swimmers must be 10. Similarly, if we know that there are exactly 20 runners over here, if we're going to take away 5 of them, then we're going to have 15 left in this region. And then, if we haven't done anything wrong, this plus this plus this should be the same thing as S or R. And in fact it is. 10 plus 5 is 15, plus another 15 is the 30 that we started with. So therefore, I hope you can see why this is actually a really useful way to count things. Now there is just one more thing to tell you, so I'm going to go ahead and show you that now. There's really no reason that we should stop at 2 sets. If we wanted to, we could continue doing this for 3, 4, and really as many sets as we wanted. We can come up with equivalent formulas to this one for sets as large as we like. So you should join us in the next lesson, where I'll actually show you how to count the number of elements in 3 sets, 4 sets, or really as many as you like. So at this point, I'd just like to summarize the lesson. In this lesson, I talked about the idea of disjoint sets, and I showed you how to count the number of elements in them. So for example, we said that this set A and B are disjoint because they share no common elements or they have no overlapping area. We said that the main reason we care about disjoint sets is because disjoint sets allow you to very easily count the number of elements in the set. So for example, if we wanted the number of elements in A or B, we would just take the number of elements in A and then add it to the number of elements in B. So for example, if we had 3 elements in A and 4 elements in B, we would just add those 2 to get 7. This formula is so handy that even if we do have sets that overlap, like this A and B over here, we decided that we would break up the sets into 3 disjoint parts, or as many as we needed. We first applied this to the set A, and then we found that we could break A up into 2 parts, A and B, which is this blue part, and A without B, which is this blue part. By doing this, we were able to assert that the number of elements in A, or the cardinality of A, is equal to the cardinality of A and B, which is this section, plus the cardinality of A without B, which is this section. We then decided to extend this to the whole overlapping set. So we said that A or B is the same thing as A and B, or A without B, or B without A. And this is actually pretty clear because there are, in fact, 3 disjoint parts, as I'm drawing right now. By breaking up the sets like this, we were able to show that A or B is the same thing as the number of elements in A plus the number of elements in B minus the number of elements in the intersection. However, once we discovered this formula, we found out that there was an easier way to get to the same answer. We saw that you could count the number of elements in A first, which gives you these 2 triangles, and then you can count the number of elements in B, which gives these 2 circles. And then, since we double counted the middle section, we could subtract off the middle section 1 time. And then after this, I remarked that we could continue doing this with even more sets. So you should join me in the next lesson where I'll show you how to do 3 sets, 4 sets, or even more. But I think this is a pretty convenient ending point for this lesson on disjoint sets and counting. If you are interested in figuring out how to do 3 sets or more, you should definitely join me in the next lesson where I'll show you how to do that. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.